In this video, we'll take a look at a linear regression activity that talks about most of the ideas in Chapter 4, Sections 4.1 and 4.2. So the activity we're going to look at, we're going to read through the questions and we'll go back and revisit notes and look at a few of the items that'll help us answer these. So the data and scatter plot below represent the winning times in the women's 100-meter freestyle swimming event in each Summer Olympic Games from 1948 until now, and it's accessed from the website. Years have been scaled to years after 1900. So let's take a look at the scatter plot. This is bivariate data, which means we're taking a look at the relationship between two things. The year after 1900 for 1948 is expressed as 48 to keep the values of the independent variable a little bit smaller. The winning time was 66.3 seconds. Then, for every Olympic Games up until 2016, with a time of 52.7 seconds, is recorded. So we're taking each of these as a single coordinate and making a scatter plot. So each of the points on the graph correspond to a year after 1900 and the winning time in seconds. So what we want to do is, we've got the scatter plot. What we'd like to do is that notice that years after 1900 are on the horizontal axis, winning times are on the vertical. So that makes years after 1900 the independent, time the dependent variable. Describe the relationship between the two variables shown, including pattern and association. So pattern part is there a pattern in the dots? So it looks like it could be linear. It also looks like it might level off a little bit and maybe be a curve. We're doing linear regression, so I'm going to write that I think the pattern might be linear, and then we're going to describe the association. Okay, so, and when you do this on an assignment, use full sentences, okay? So I'm going to describe it as linear, so write more than I do. And then describe the pattern and association. When you look at the notes for Chapter 4 on our scatter diagram, two variables that are linearly related are positively associated if, and I'm going to skip down to the last sentence. They're positively associated if, whenever the value of one variable increases, the value of the other variable also increases. They're negatively associated if, when the value of one variable increases, the value of the other variable decreases. So is it a positive or a negative association? So in the activity, notice that as the years increase, the times are decreasing. So this would be a linear negative association. And then explain why that is. As the years increase, the winning times decrease. Okay, so now that we've looked at our pattern of linear negative association, now we know that we can use linear regression because we've got a linear pattern in our graph. So for part B, we're going to use technology to find the least squares regression line and the correlation coefficient. So this part is actually just typing it in and using technology to do the work. So I've got the data entered in StatCrunch. So let me go retrieve that. We've got years after 1900 entered in the first column, time in seconds entered in the second column. So to have StatCrunch find your line of best fit, we're going to look at Stat, select regression, and we're doing simple linear regression. So click. Our X variable, we're going to use years after 1900. That's our independent. Our Y variable is time in seconds. Then there's a lot of questions that are asked below here. There are a lot of things we just haven't done yet. We don't know anything about the hypothesis tests. So just scroll down. What we can do is if you want to, you can put an X label, axis label. So I'm going to go ahead and make that years after 1900. The y-axis label. It's not Arizona population in millions. This time it's winning times. Oops, where did it go? I didn't want to hit that yet. Hang on. Let me close out of that and do that again. All right, so we're on regression, linear, x variable, y variable. Okay, so I was typing in the x-axis label. You can type in years after 1900. You can type in for the y-axis, type in time in seconds. You can put a title, and the title would be Olympics. Okay, I'll leave that to you. You have to do that on the tech lab, but this is just an example. Okay, click on compute. And I want to take a look at the printout. So how do you know what your line of best fit is? So where it is located is right on the time in seconds. It's got this 73.05419 minus 0.19218 times years after 1900. So it's not exactly in the format that our textbook has, but also down below it says the intercept estimate and the slope estimate. We've also got the correlation coefficient as an output on StatCrunch. So I want to take that information and I'm going to go back and write it down on our Word document. So I need to move this, and so I can get to the Word document. I'm going to go to 2 spaces. I'd go to however many spaces MyMathLab asks you to. I'll go 3 spaces on the correlation coefficient. So I'm going to go back to the Word document, and we're going to write down the least squares regression line and correlation coefficient that StatCrunch gave us. So the least squares line is in the form of y hat is equal to b1 times x plus b subscript 0. So from our printout, y hat equals the slope, which is rounded to 2 places, negative 0.19x, plus the y-intercept, rounded to 2 places, which was 73.05. The correlation coefficient, r, is equal to a negative 0.925. If your slope is negative, your correlation coefficient will be negative. So what did that just do? So I'm going to go back to our printout from StatCrunch. The second is a visual of graphing your line through the points. So what a line of best fit does is takes the distance between each of your points in the line of best fit, and it makes it as small an error as possible. So that line has been fit in between there so that the distance, the error between the points in your actual data and the points on the line and the line, distance to the line, is at as small an error as possible. So that's our line of best fit. And you'll notice about half of the points are above the line, half are below, and some of them look like they're pretty close or right on the line. Okay? But they don't fit perfectly. So now when we go back, Part C says identify the slope in your least squares regression line and describe what it represents using appropriate units. Slope is rise over run. So this y hat equals a negative 0.19. That's a negative 0.19 over 1. So what are the measurements that we're using? Let's get a little bit more room here. The measurements that we're using for the vertical axis are seconds, and the measurements that we're using for the horizontal axis are years. So this says that for each year, the Olympic times are decreasing by about 0.19 seconds per year on average. So the slope is an average, it's not exactly. So the sentence that we would say is winning times are decreasing by an average of 0.19 seconds per year. And put the data that we have. What years do we have? From 1948 to 2016. So that's the interpretation of the slope. Then part D, is a linear model a good fit for this data set? Why or why not? So we have to use the correlation coefficient table to justify our answer. So we know that our R value is close to 1 because our R value was negative 0.925, but we have to take that one step further. How do we know that that's good for the data that we have? So I'm going to go back to notes. These are posted in Canvas. The correlation coefficient is between -1 and 1. So there are examples on notes what perfect 1 means, perfect -1, and then how to tell whether a line is a good fit. So testing if you have a linear relation. Step 1, determine the absolute value of your correlation coefficient. Then find the critical value in the table for the given sample size. I put the table on your notes and it's also posted in Canvas. We have 18 data values in our set, 18 points. So this says the critical value is a 0.468 in the table. So what we're going to do is compare that. If the absolute value of our correlation coefficient is greater than the critical value, then yes, we have a linear relation. So that 0.468 tells us that yes. So the answer is yes. The absolute value of our correlation coefficient of 0.925 is greater than the critical value of 0.42, what was it, 0.428? 0.468. So you would write that in the sentence. So the answer is yes, because the absolute value of our correlation coefficient is greater than the value in the table for n is equal to 18, which is 0.468. All right, so if a line is a good model, then we can use it to make some predictions, or we can use it to make some estimations. So part E says use your linear model to estimate the winning time in the 1996 Olympics, and then compare your estimate to the actual value in the table above. So I'm going to use the line y hat is equal to negative 0.19 times 96 plus 73.05, and I want to see what that ends up being. So throw that in the calculator. If we would round it to a few more decimal places than 2, we'd get probably a more accurate answer, but it's okay for our purposes now. So negative 0.19 times 96 plus 73.05 is equal to 54.81 seconds. So our line predicts 54.81 seconds. What was the actual time from the table? So in 1996, the actual time was 54.5 seconds. So our line overestimated. So when you compare your estimate to the actual, then our line, our model, overestimated 54.81 seconds, and actual was 54.5 seconds. And that makes sense, because usually it's not going to be exactly what's in your data set. It's an average. Okay. Next question, use your linear model to estimate the winning time in the 2032 Olympics. Do you think this prediction is reasonable? Why or why not? So we're going to use our line again, our y hat. We have to convert to years after 1990. This is 2032, so that would be 132 years after 1900. plus 73.05. So we enter that in the calculator and see what the prediction is. And we end up with 47.97 seconds. We don't have an actual value to compare it to, so we want to talk about a little bit, is that reasonable or not? So let's look back at the graph and the line. So if you're taking a look, notice our line fits pretty well for some of the points, but notice the times start to level off later in the year. So if we were to extend this line to 132 and get 47 seconds, it's probably faster. It might not be a great prediction, mainly because it's a little bit too far out of the range of our data. So for prediction purposes, lines of best fit are pretty good if you're going just a little bit beyond your data set on either end, but not so good if you're trying to predict far in the future. So it's two reasons. We've got a value a little bit too far in the future outside of our data set, and also that our data set, the last few numbers started to level out, and our line really predicts a much faster time than actual. So you would write that as your solution in part F. So the answer, prediction is not reasonable. And then you would say for the two reasons that we talked about. Either it's too far outside our data set, 2032 Olympics is 16 years from now, and also those points, our line was looking at times as being much faster. All right, last item that we're going to look at is, what if your line is not a good fit? What if you can't plug the value in and use your line to predict? So this will happen sometimes, that you look at your data and you end up with a line that isn't, the linear model just doesn't fit. So you can't use the line to predict. So what we do, I'm going to take you to notes where this is, and it's important. So if the correlation coefficient indicates no linear relation between your two variables, and the scatter diagram indicates no relation at all between the variables, then you use the mean value of the response variable as the predicted value. So you don't use the equation to predict, you use the mean of the y's. So what does that mean? So back here, if a line was not a good fit and it said use your linear model to estimate the winning time, 96, you wouldn't plug 96 in. You would take a look at your data and you would find the mean of the y. So remember how to do that. It's summary statistics of the time in seconds. The mean. The mean is about 57.295 seconds. So your prediction, no matter what they asked you to put in for x, if a line's not a good fit, your answer would be the mean, which was the 57.295 seconds. That would be your answer for both E and F, and that might happen on homework. If a line's not a good fit, use the mean of your dependent variable, and that's your prediction no matter what your x value is.